Okay, so let's walk through the types of orders that we will be discussing. There are three, and of course there are more, but we're just interested in explaining the three orders: zero, first, and second. And this video walks you through what you're responsible for in terms of the rate law and the corresponding concentration versus time, and rate versus the concentration of C. So when we see this information, you're now responsible for observing that if you have a zero order, this is the rate law. It's actually the relationship that you can get. It's called the integrated rate law, and it is in fact the way that you can calculate the concentration of C at any time t, given the initial concentration. We also have this form for the first order relationship, in which it's the same. Given any C0 and any K, you can plug in a time t and you can calculate the concentration C. And for the second order, we can see that we have a similar relationship. And these three all give us insight into one, what is the form the concentration takes with time, and two, what kind of relationships will we need to make mathematically so that we can extract the rate constant K. This is important because we want to be able to calculate the concentration at any time t. So let's look closer at the first order, at the zero order reaction. So here is our rate law, and concentration here with time, it is a line, right? It starts off at a concentration C0 with time, and then is linear. Linear because the time is linear with respect to concentration, and the slope is minus k. That should be clear and straightforward based on the relationship that we see here, where we see C0 is in the form of b, the intercept, and minus k is the slope, and time would be an x variable if we were going to put it in the standard format. If we were to look at the rate of the chemical reaction as a function of the concentration C, we would see a straight line because the slope or the rate of reaction doesn't change with concentration. It's in fact independent. This would be shown here as the rate of the chemical reaction for a zero order is the change in C with respect to time, and it equals just the rate constant K. It is in fact times the concentration of C to the 0 power. This is the origin of its name, zero order, but we see that it's completely independent of C. So let's take a look at the first order chemical reaction a little clearer. So here we have the relationship between concentration and its initial concentration and its rate constant K. At any time t, if we could find the rate constant K and we had initial concentration C0, we could then calculate the concentration at some time later. This is first order. So the graph of concentration versus time is not going to be linear. It's going to have a C0, and there's going to be an exponential decay. It's going to be curvy. And to get the rate constant from this data set can be quite difficult. Now calculators can be able to do it if you're able to fit this to an exponential. But we'll take advantage of the linearizing effect of taking the ln, which is also this is a common theme that we've done in class. So we have the ln of concentration, we have the intercept, which is the ln of C0, and then we have a straight line. The straight line is now minus K. And if we were to make a plot of the concentration of C, the rate versus the concentration C with first order, we would see a nice straight line with a slope of K. And to show why that's the case, we would look at the rate law, which is the rate law for first order. And so we would look at the concentration of C with respect to T, which is the rate, the velocity of the reaction, is going to be equal to K times the first order, right, the first power of C. So that's why we would see a linear relationship of the rate of the chemical reaction with C. Okay. So let's take a closer look at the second order chemical reaction, which is here. This is its rate law, and it has, again, the form that if we knew C0 and we had the rate constant K, at any time T, we'd be able to calculate the new concentration. This is what's called second order, based on its rate law. Okay, so let's do that. Let's take a look at the concentration of C with time. And we see this is also curvy. And as a matter of fact, by eye, it's almost impossible to be able to discern or distinguish a first order from a second order because it is also curvy. But mathematically, we should be able to determine the difference between the two because one will fit a 1 over concentration with time. If we plot the 1 over concentration versus time here, we will get a point on the y-axis, which is going to be 1 over C0, the intercept. And then we see a straight line with a slope equal to K. If we were to now plot the rate of the chemical reaction versus the concentration C, we would get what looks like a quadratic formula, starting at 0 and going up in a quadratic manner. This is because the rate law is equal to the change in concentration with respect to T, and for a second order reaction we have quadratic behavior. So this quadratic behavior is what gives the rate versus concentration its distinction, just as if we were graphing y equals x squared. Okay, so summarizing what you are going to be responsible for here is you have the zero order, the first order, and the second order. You're going to be responsible for the rate law, the concentration versus time graph. Let me make that a little bit nicer. It's going the rate law, the concentration versus time graph, and of course the rate versus concentration graph. You're responsible for all three given these different rates. In another video we will talk about how do we get whether it's zero order first, or how do we get the order from the data or from, let's say, detailed information about the molecularity of the slow step in a mechanism. But for now, once we know we have the rate law, this is what you're responsible for. So the rate law for zero order is K. The rate law for the first order is K times the concentration to the first power, and for the second it is the power 2, right? So it seems reasonable given second order you'd have that power 2. And if we look at the concentration versus time for zero order, we see a nice straight line with the slope minus K. We do the same thing, concentration versus time for first order and for second order, and we see that these are both curvy. You have to make the appropriate calculations. For the first order, it's going to be the ln. For the second order, it's going to be the reciprocal to make it a linear plot as discussed earlier. You are also going to be responsible for determining the rate versus concentration for each of the orders. So let's take a look. This is going to be the zero order because the rate itself versus concentration does not depend. It's independent of the concentration, while the first order is linear with this, like as if we were plotting y equals kx. And then we see a quadratic relationship in the rate versus concentration for second order. Okay, so R versus concentration of C for each of the orders. You should make sure that you can reproduce this particular image and be able to describe how and why you would get this relationship.